Imagine you break your arm, you go to the hospital, the doctor takes an X-ray, and there on the film is a jagged white line.
Right, it's undeniable.
Yeah. The doctor points to it and says, "There it is." And it's a comforting moment in a strange way because it's binary. The bone is broken or it is not.
I mean, a wall is made of bricks. The bricks hold still, so the wall holds still.
Exactly. When we look at the physical structure of the world, especially the macroscopic world we interact with every day, there's this ingrained expectation of precision, like engineering.
Well, we crave that structural stasis, you know? We want the building blocks of reality to be visible, to be neatly categorized.
Yeah, we want them to follow the rules.
Right. To faithfully follow the macroscopic rules of physics that our human brains actually evolved to understand. It gives us a sense of control over our environment.
But step into the microscopic world of biology, into the very architecture of a living cell, and suddenly that X-ray machine of human intuition completely breaks down.
It shatters, honestly.
If you look closely enough at the structural landscape of living matter, you aren't looking at still bricks. You are looking at a boiling, chaotic storm of particles.
Absolute thermal chaos.
And yet somehow, out of that violent microscopic storm, we get the absolute magnificent precision of a living, breathing, thinking human being.
It is the ultimate paradox.
Welcome to today's deep dive. I am incredibly glad you are joining us because we are going to explore a single mind-bending source text that completely revolutionized how humanity understands the boundary between dead matter and living beings.
It really is a foundational piece of work.
The book is called What is Life? It was published in 1944, and it was written by the Nobel Prize-winning physicist Erwin Schrödinger.
And it's difficult to overstate how critical this text is to modern science. What makes this book so utterly fascinating is the context of its creation.
Right, because he wasn't a biologist.
Not at all. Erwin Schrödinger was a theoretical physicist. He was literally one of the founding fathers of quantum mechanics.
Dealing with wave functions, not cells.
Exactly. He spent his life dealing with mathematical wave functions and subatomic particles, not fruit flies and cellular tissue.
He is stepping completely out of his lane here, and he knows it. I mean, in the preface to the book, he actually apologizes for it.
Yeah.
He says he is deliberately renouncing his noblesse oblige. That's the sort of unwritten, gentlemanly rule in academia that a scientist should only ever write or speak publicly about the specific, narrow topic they are a recognized master of.
Which was a huge deal back then.
Oh, massive. Schrödinger is taking a huge professional risk by doing this. He is essentially risking making a fool of himself in front of the world's leading biologists by stumbling into their territory.
But he tells the reader exactly why he feels compelled to do it, right?
Yeah, she argues that the modern dilemma is that human knowledge has become too specialized.
The multifarious branches of science had gotten so deep and so narrow by the mid-20th century that it was becoming almost impossible for a single human mind to see the whole picture anymore.
Everybody was just in their own silos.
Precisely. The physicist knew nothing of heredity, and the biologist knew nothing of quantum states. Schrödinger believed that someone eventually had to take the leap to synthesize it all.
Someone had to try to weld together the facts and theories from physics and biology into one cohesive understanding.
Even if they had to rely on secondhand knowledge to do it.
Okay, let's unpack this. What exactly is the central mystery he is putting his reputation on the line to solve?
Well, Schrödinger boils the entire endeavor down to one incredibly difficult question.
Which is?
How can the events in space and time, which take place within the spatial boundary of a living organism, be accounted for by physics and chemistry?
In other words, if we are just made of atoms, can physics explain us?
Right. And my preliminary answer to that, and the answer Schrödinger offers right at the outset, is this. The obvious inability of present-day physics and chemistry to account for those events is no reason at all for doubting that they ultimately can be accounted for by those sciences.
So just because they couldn't explain life in 1944 doesn't mean it's impossible.
Exactly. That failure was not because life operates on magic. It was because the arrangements of the atoms in the most vital parts of a living organism are fundamentally different from anything physicists had ever previously studied in a laboratory.
It's like a totally different architecture.
It is. The architecture of life is playing by a set of physical rules that traditional classical physics had simply never encountered in inanimate matter.
It's such a wild, ambitious premise. To figure out how living things operate, Schrödinger says we first have to pretend we know nothing about biology.
We have to adopt the view of what he calls the naive physicist.
Right. We have to deeply understand the chaotic rules governing dead, inanimate matter first, before we can understand how life manipulates those rules. And he starts this entire journey with a question that sounds almost like a child's riddle,
Yeah, he asks, why are atoms so small?
which is naturally an illusion of the real issue.
Because atoms are just what they are. They're the baseline.
Exactly. The real question, as he points out, is why are we so big? Why must our bodies, and specifically our brains and our sensory organs, be so incredibly massive compared to the size of a single atom?
Why did nature build you and me out of trillions upon trillions of these tiny building blocks, rather than just, a few thousand?
To help you truly grasp the scale we are dealing with here, Schrödinger references an analogy originally posed by Lord Kelvin. It is a brilliant, staggering thought experiment.
It really puts it into perspective.
Suppose you could take a single normal-sized glass of water, and somehow you have the ability to paint a tiny little red mark on every single individual water molecule inside that glass.
I am picturing a very tiny paintbrush, but okay, I have my glass of physically marked water.
Right. Now, you take that single glass of marked water, you walk down to the beach, and you pour it out into the ocean. Then you stir the ocean.
That's a lot of stirring.
You stir all the water on Earth. You mix the Atlantic, the Pacific, the Indian Ocean, the Mediterranean Sea. You stir it so thoroughly that your marked molecules are perfectly uniformly distributed across the entire globe.
That is a phenomenal amount of mixing. The ocean is incomprehensibly vast.
Indeed. Now, after you have completely stirred the seven seas, you go anywhere in the world. You fly to the coast of Japan, or you go to a beach in California, and you dip a regular glass into the ocean and scoop up some water.
Okay, I have my new glass.
How many of your original red-marked molecules do you think you would find in that new glass?
I mean, intuition screams that the answer has to be 0.
Right. The ocean is too huge, and a glass of water is too small. The dilution should be absolute.
But the mathematical reality is that you would find about 100 of your marked molecules in that new glass.
Wait, really? 100?
Yes, about 100. Any random glass you scooped out of the ocean anywhere on Earth would contain 100 of the exact molecules from your original glass.
That is how mind-bogglingly vast the number of molecules is in a single glass of water.
It vastly outnumbers the number of glasses of water in the entire ocean. The size of an atom is so infinitesimally small that an object just barely recognizable under a standard microscope still contains thousands of millions of atoms.
So we return to the child's riddle. Why must we be so gigantic compared to these atoms? Think about it. Wouldn't it be an evolutionary superpower if our senses were fine-tuned enough to feel the impact of a single atom?
Or if our ears could hear the vibration of a single molecule in the air.
Exactly. Why did nature mandate that we will be massive, lumbering giants made of trillions of parts?
Well, this forces us to look at a fundamental necessity of physical law. If we were sensitive to the impact of a single atom, or even a few atoms, life as we know it, and specifically the phenomenon of orderly thought, would be completely physically impossible.
Okay, let's drill down into that. Why would orderly thought be impossible?
Because of a phenomenon known as heat motion or thermal chaos.
The constant movement.
Right. In the macroscopic world, things can hold still. In the atomic world, atoms are never, ever still. Unless they are frozen at absolute zero, which is negative 273 degrees Celsius, atoms are constantly moving.
They are violently vibrating, bouncing, spinning, and smashing into each other.
Yeah. The ambient heat of the room you are sitting in right now is just the aggregate kinetic energy of air molecules zipping around and colliding. It is a state of perpetual, completely disorderly thermal chaos.
So imagine if your brain and your sensory organs were composed of just a few dozen atoms. Your physical state would be entirely at the whim of this erratic, microscopic demolition derby.
Precisely. If your brain were sensitive to single atoms, a single stray impact from a vibrating oxygen molecule in the air could just blast into your sensory receptors and completely derail your entire train of thought.
So thought requires order.
It does. What we call thought is a highly orderly process. It requires a correspondingly highly well-ordered physical organization in the cellular structure of the brain to run in parallel with it.
Furthermore, the brain must process material perceptions, sights, sounds, and experiences from the outside world that also possess a high degree of physical orderliness.
You simply cannot maintain strict physical laws or orderly biological processes in a system governed by a tiny number of violently unpredictable particles.
It makes me think of a swarm of angry bees.
Oh, that's a good analogy.
Yeah, like if you are standing right in the middle of the swarm, zoomed in on just one or two bees, It is pure, terrifying chaos.
Yeah.
One bee is darting left, one is diving right.
Bumping into each other, spiraling randomly.
Exactly. You have absolutely no way to predict what any single bee is going to do in the next half second. But if you step a mile away and you look at the swarm as a whole massive unit against the sky, you don't see the individual chaotic movements anymore.
You just see a single dark cloud.
Right. Moving smoothly, purposefully, and predictably toward a tree.
That is a wonderful visualization of the mathematical heart of statistical physics. What Schrödinger is demonstrating is that the laws of physics and chemistry, the laws that govern our bodies, the structural integrity of our buildings, the flow of rivers, are all statistical laws.
They aren't absolute dictates.
No, they are not absolute dictates that apply to individual atoms. They're only accurate when you have an enormously large number of atoms cooperating together.
Because the massive numbers average out the chaos. The bee darting left cancels out the bee darting right.
Yes, and statistical physics actually gives us a formula to calculate exactly how much chaos remains based on how many atoms are involved. It is called the square root of n rule.
The square root of n.
Right. This rule tells us the exact degree of inaccuracy we can expect in any physical system. If n is the total number of cooperating atoms in your system, the relative error, or the departure from the predictable physical law, is mathematically proportional to 1 over the square root of n.
Let's do the math on that for you listeners so we can really see why size matters. Let's say you have a tiny biological process in a cell that relies on just 100 atoms. So n equals 100.
Where?
The square root of 100 is 10. That means your error rate is 10 out of 100, which is 10%. A 10% margin of error for a foundational law of nature.
A 10% unreliability rate would be catastrophic for a biological mechanism. Imagine if your heart beat incorrectly 10% of the time.
Or if your cells failed to divide properly 1 out of every 10 tries, life would disintegrate instantly.
But let us scale it up. Let us increase n to 1 million atoms. The square root of a million is 1,000. So the error is now 1,000 out of a million, which is 0.1%.
The error rate plummeted just by adding mass.
Exactly. As the number of atoms grows into the billions and trillions, the relative error shrinks towards 0, and the statistical average becomes an incredibly precise, reliable physical law.
That is the fundamental reason our bodies must be macroscopic.
Yes, we need billions of atoms in every single cell just to buy ourselves the luxury of exact physical laws. We have to be massive to escape the deafening statistical noise of the micro world.
To really drive this home, Schrödinger gives a few incredible examples of this statistical physics in action. Let's look at paramagnetism.
A classic example.
He says if you put oxygen gas into a magnetic field, the gas actually becomes magnetized. And the reason is that every single oxygen molecule acts like a tiny little compass needle.
The magnetic field is applying a force, trying to pull all those millions of microscopic needles to align perfectly parallel to the field.
However, if you observe this in reality, they do not all snap into perfect alignment instantly, do they?
They don't. Because the heat motion, the chaotic bouncing and vibrating of the atoms, is constantly fighting against the magnetic field.
The ambient heat is trying to knock the molecules out of alignment and randomize them, while the magnet is trying to organize them.
So what you end up getting is just a slight statistical preference for the atoms to face the right way. It is a literal physical tug of war between order and chaos.
But here is the mechanism that proves the rule. If you artificially lower the temperature of the gas, you are slowing down the heat motion.
The thermal chaos gets weaker because the atoms have less kinetic energy.
And as the chaos weakens, the magnetic field starts winning the tug of war, and the overall magnetization of the gas gets stronger. This is known as Curie's law.
It beautifully proves that the macro-level physical law is entirely dependent on the average behavior of millions of molecules fighting against random thermal chaos.
He provides another equally compelling example, right? Brownian movement.
Yes, which we often observe as diffusion. Imagine you have a clear glass vessel filled with water. You carefully introduce a single drop of a deeply colored substance like potassium permanganate on the far left side of the vessel.
Okay, I can picture that.
If you watch, gradually, the purple color spreads out until the entire vessel of water is uniformly tinted.
If you've ever dropped food coloring in a glass, you've seen this. It looks like the purple molecules are actively walking away from the crowded area where they started, migrating toward the empty space on the right side.
Like people spreading out to find breathing room in a crowded party.
Exactly. It looks purposeful, but it is not.
There's absolutely no attractive or repulsive force driving those purple molecules apart. Every single potassium permanganate molecule is completely blind to its neighbors.
It is simply being violently knocked around by the invisible water molecules in completely unpredictable, random directions.
It is akin to a blindfolded person taking a step in a totally random direction every single second.
So how does a totally random blindfolded walk result in a perfectly smooth, predictable diffusion from high concentration to low concentration?
Because of the inescapable logic of statistics. Imagine drawing an invisible line down the middle of the water. On the left side, where you drop the die, you have 100 purple molecules doing a random blindfolded walk.
And on the right side, you only have 10 molecules doing the same random walk.
Right. Purely by chance, in the next second, more molecules will stumble across that invisible line from left to right than from right to left.
Not because they possess a desire to go right, but simply because there are vastly more of them on the left available to make the stumble.
The macro-level law of diffusion is mathematically elegant and perfectly predictable, but if you zoom in, it is built entirely on the foundation of pure, blind atomic chance.
And the third example he gives is where this principle actually becomes a headache for scientists. It involves an instrument called a torsional balance.
Yes. Torsional balances.
Physicists use these incredibly delicate, feather-light bodies suspended on microscopic fibers to measure ultra-weak forces like faint gravitational poles or tiny electrical charges.
But scientists quickly discovered a hard physical limit. If you make the measuring instrument too light and the suspending fiber too thin, something crazy happens.
The instrument itself begins to dance.
Yes. You look through the magnifying glass, and the suspended weight is trembling and twitching irregularly, darting back and forth, even when there is absolutely no magnetic or gravitational force being applied to it.
Why? Because the instrument has become so incredibly delicate and lacks so much mass that it is actually feeling the ambient heat motion of the surrounding air molecules hammering against it.
The macroscopic world has finally breached the microscopic.
And that square root of n rule is failing right before your eyes. The statistical law breaks down because the physical instrument simply does not have enough billions of atoms to absorb and average out the chaotic collisions.
The overarching point Schrödinger is cementing here is crucial for you to internalize before we move forward. He's just proven, with absolute classical physical certainty, that exact, reliable laws require billions of atoms.
If you only have a few dozen or even a few thousand atoms, they are completely at the mercy of boiling thermal chaos.
They will dance randomly like the torsional balance. They cannot hold a stable, rigid shape, and they most certainly cannot reliably store, protect, or transmit orderly information.
Which sets up what might be the greatest scientific contradiction of the 20th century. Because we just firmly established the ironclad rules of inanimate matter, but now we have to look at living matter.
We're going to zoom deep into the biological mechanism of heredity.
And when we do, that unbreakable statistical rule doesn't just bend, it completely shatters.
Let us examine the biological entity responsible for life, the hereditary code script, the chromosomes.
To lay the groundwork here, we all start our lives as a single fertilized egg cell. And inside the nucleus of that single cell are chromosomes. In humans, we have 46.
Schrödinger, writing in 1944, specifies two sets of 24, one from the mother, one from the father.
Right. Today, modern science knows it's actually 23 pairs, but the physical principle he describes remains exactly the same.
What is remarkable is how Schrödinger conceptualizes these chromosomes. He insists they are not merely a passive blueprint, like a set of architectural drawings waiting for someone else to build them.
They are the law code and the executive power rolled into one.
He calls them both the architect's plan and the builder's craft. They do not just contain the inert information of whether a person will have blue eyes or a physiological predisposition to asthma.
They actually possess the operative mechanical power to manifest those features.
And as this single cell begins to grow into a human being, it undergoes a process of cell division called mitosis.
The single egg divides into two cells. Those two divide into 4, then 8, 16, multiplying until you have a fully formed infant.
But the key is what happens right before the cell divides. The entire double set of chromosomes is meticulously duplicated.
Every single one of the trillions of cells in your body contains the exact same, complete, unaltered double copy of the original code script. I love the analogy he uses here, drawing from the news of his era.
Military analogy.
Yeah. He compares it to General Montgomery in the North African campaign during World War II, making absolutely certain that every single private soldier in his entire army is meticulously informed of the entire overarching strategic battle plan.
It is a staggering feat of biological logistics. And the only time the body deviates from this exact double duplication occurs during reproduction in a specialized process called meiosis.
The reductive division.
Correct. When the human body creates gametes, which are the sperm or egg cells, the double set of chromosomes finally separates.
So the resulting gamete only receives one single set of chromosomes.
It is haploid, meaning single, whereas normal body cells are diploid, meaning double. Therefore, when fertilization eventually occurs, the male haploid set and the female haploid set fused together to create a brand new diploid individual.
This elegant mechanism ensures the offspring receives exactly 50% of its genetic code from each parent.
But the mix from the grandparents is where the chaos of chance enters the biological picture. Because when that double set of chromosomes separates during meiosis to make a sperm or an egg, it is effectively a 50-50 coin flip, whether you pass on the specific chromosome you inherited from your dad or the one you inherited from your mom.
And nature makes it even more complex with a phenomenon called crossing over.
Right. Before the chromosomes separate, the homologous pair, say, the pair of chromosome number 7, will physically wrap around each other and swap entire chunks of data. They shuffle the deck.
If we pause and connect this biological mechanics back to our physics discussion, we realize something profound. All of these incredibly intricate biological processes, mitosis duplicating the code, meiosis having it, crossing over, shuffling it, are physically manipulating a material structure.
The gene is a physical object holding hereditary information. And this tiny physical object possesses an astounding, almost miraculous permanence.
The permanence is the part that breaks the physicist's brain. To illustrate this, Schrödinger brings up the famous Habsburg lip.
A very visible historical example.
Yeah, this was a specific, distinctively protruding lower lip that was passed down through the royal Habsburg dynasty in Europe for centuries. Biologists actually traced its inheritance through historical royal portraits.
For hundreds of years, generation after generation surviving through countless thousands of cell divisions, shuffling, and recombinations, this exact microscopic code for a deformed lip was faithfully, flawlessly reproduced.
Now, consider the physical environment this gene was kept in for those hundreds of years. It wasn't sealed in a vacuum or frozen in a cryogenic vault.
No, it was kept inside a living, breathing human body at 98 degrees Fahrenheit.
98 degrees Fahrenheit. If you are a physicist looking at that temperature, that is a boiling cauldron of thermal chaos.
The atoms at 98 degrees should be vibrating and smashing into each other violently.
This raises an important question. This is the core biological paradox Schrödinger has identified. How large is this gene?
How much mass does this physical object have that it can survive the boiling chaos of 98-degree heat motion for centuries without its shape decaying or its information scrambling?
Schrödinger looks at the scientific estimates available to him. First, he looks at genetic breeding experiments, where scientists map the physical distance between traits on a chromosome based on how often they are separated by that crossing over process we mentioned.
Then, he looks at microscopic inspections done by a scientist named Darlington.
Darlington used a microscope to look at the salivary glands of the Drosophila, the common fruit fly.
He used the salivary glands because in fruit flies, those specific chromosomes are enormously enlarged, making them easier to see. He counted the dark bands on the chromosome fiber, measured the length, and divided it out.
Darlington actually did the math on this physical structure, and the number he came up with is genuinely terrifying for a classical physicist.
The maximum size of a single gene, according to Darlington's measurements, is a cube with an edge of 300 angstroms.
Let's translate that into terms you can actually visualize. 300 angstroms is incredibly microscopically small.
It's only about 100 to 150 atomic distances across. That means a complete gene, the physical structure dictating a human trait, contains at absolute maximum about 1 million atoms.
And likely far fewer than that.
We must pause here and heavily weigh the gravity of that number. 1 million atoms.
We just established mathematically, using the square root of n rule, that to have a reliable physical law that can resist the chaos of heat motion, you need billions of atoms.
1 million atoms is entirely too small to follow this statistical rule. A million atoms is a tiny microscopic speck. It should be dancing and trembling wildly like the torsional balance.
And it gets worse for the physicist, because it isn't like the gene is a homogeneous drop of liquid where all 1 million atoms are just interchangeable water molecules doing the same thing.
Every atom, every chemical radical, which is a specific group of atoms bonded together that act as a single unit in chemical reactions, every piece of this gene is playing a highly specific individual structural role.
If you move one piece, the information changes. So the paradox is staring us right in the face. We have a physical structure way too small to rely on the safety of large numbers, kept in a 98-degree chaotic heat bath, and yet it dictates the precise physical development of a human being and maintains its shape flawlessly for centuries.
How does it not melt down?
To figure out how the gene maintains this impossible ironclad stability, Schrödinger realizes we cannot just look at the normal genes. We have to look at the rare, exceptional moments when that stability actually fails.
We must look at mutations.
Which brings us to the jump-like mutations. And this requires a bit of a historical pivot because we have to correct a slight misconception introduced by Charles Darwin.
Darwin, as brilliant and foundational as his work was, believed that evolution worked constantly on small, continuous, accidental variations within a species. He thought nature was always smoothly sliding forward.
But Schrödinger points out that Darwin was mistaken on this specific physical mechanic of inheritance. Continuous, smooth variations are actually not inherited at all.
He gives the example of a barley crop to prove this. Imagine you are a farmer with a field of purebred barley. If you walk through the field and measure the length of all the awns, those are the little hair-like bristles sticking off the ears of barley, you will get a standard bell curve.
Most of the bristles are an average length. Some are exceptionally short, and some are exceptionally long.
Darwin's theory suggested that if you only harvest the seeds from the barley with the absolute longest bristles and plant only those seeds next year, your new crop will smoothly shift. The new average length will be longer.
It seems perfectly logical, but if it is a truly purebred strain, experiments prove that this does not happen. The new crop, grown only from the longest bristled parents, will produce the exact same bell curve with the exact same average length as the original crop.
The continuous small variations in the parent's bristles were just environmental accidents. Maybe that specific plant got a little more water or a little more sunlight.
Those variations were not physically written into the hereditary substance.
So evolution seems stuck. Until 1902, when a Dutch botanist named De Vries discovered something monumental. He found that even in those perfectly purebred plant stocks, a tiny rare number of individuals, maybe 2 or 3 out of tens of thousands, would suddenly appear with small but jump-like changes.
These changes were completely discontinuous. There were no intermediate forms between the normal plant and the changed plant. It didn't grow slightly longer bristles. It suddenly had no bristles at all.
It was an all-or-nothing discrete jump. De Vries called this phenomenon a mutation.
And crucially, unlike the smooth environmental variations, these jump-like mutations are perfectly inherited. If you take that mutated bristleless barley plant and breed it, all of its descendants will be bristleless.
This discontinuous jumping is the true physical working ground of natural selection. Evolution is not a smooth ramp of gradual change. It is a staircase.
A species waits on a step for a random mutation to physically jump it to a new step. And if that new step provides a survival advantage in the environment, the new trait breeds true.
It is so fascinating because any physicist reading De Vries's work on jump-like discontinuity immediately thinks of one specific thing.
Yeah, De Vries himself actually called his discovery, figuratively speaking, the quantum theory of biology.
Because in quantum physics, energy does not move on a continuous ramp. Energy jumps between discrete levels with absolutely no in-between states.
De Vries meant it purely as a poetic metaphor. But as we will soon see, decades later, Schrödinger takes that metaphor and mathematically proves it is literally, physically true.
But before we dive into the quantum physics of the molecular bond, we need to understand how these mutations function within a living population. And this leads us to the biological danger of close breeding.
We have to talk about dominant versus recessive traits. When a mutation happens, it typically only happens in one chromosome of the pair. Let's say a father develops a new mutation in his sperm cell, but the mother's egg has the normal original version of that gene.
When they fuse, the child has 2 different versions of the same instruction manual. These different versions are called alleles.
Now the body has to decide what to do. One of these alleles is going to act as the boss. It will be dominant, and its instructions will be billed. The other allele will be ignored. It becomes recessive.
It turns out that the vast majority of mutations are recessive. And furthermore, the vast majority of random mutations are harmful.
If you pause to think about it, this makes intuitive sense. If you have a highly complex, beautifully ordered machine like a watch or a human cell, and you make a completely random blind change to one of its gears, you are much more likely to break the machine than to miraculously improve it.
But because these harmful broken mutations are almost always recessive, nature effectively hides them. The organism is what biologists call heterozygous for that trait, meaning it carries one normal allele and one mutated allele.
The normal dominant allele steps up and does 100% of the work. The organism appears perfectly healthy, functions normally, and survives, but deep inside its cellular vault, it is secretly carrying a broken piece of genetic code.
This specific biological mechanic is exactly why close breeding or incest is so biologically perilous. Schrödinger takes the time to walk the reader through the chilling mathematics of this because it beautifully illustrates probability.
Imagine you are carrying a hidden, harmful, recessive mutation. You don't know it because your dominant allele keeps you healthy. If you go out into the world and marry a complete stranger, the statistical chances of that stranger carrying that exact same rare, specific mutation are incredibly low.
Your children might inherit your broken mutation, but they will also inherit a healthy, normal allele from your spouse. So the disease remains hidden and the child is healthy.
But what happens if you marry within your own bloodline?
Let us calculate the specific danger for first cousins. You have a hidden mutation. By the laws of meiosis, half of your children will carry it. If they grow up and marry strangers, a quarter of your grandchildren will carry it.
But if two of those grandchildren who are first cousins to each other marry each other, what are the mathematical odds that their future child will actually physically manifest the hidden disease?
For the disease to manifest, the child must inherit the broken allele from both parents. They both have to carry it. And the coin flip of meiosis has to land on the broken allele both times.
Exactly. The mathematics dictate that a marriage between first cousins carries a 1 in 64 danger factor of manifesting a shared, hidden biological defect.
And that staggering probability is just calculating the odds for one single specific mutation. Every human being on Earth is likely harboring multiple different latent recessive deficiencies.
By engaging in close breeding, you are exponentially increasing the chances that two identical broken alleles will meet in an offspring, stripping away the evolutionary protection of the normal dominant allele and bringing the disease into the light.
Nature requires these mutations to drive the staircase of evolution, but it also requires them to be incredibly rare, so a species doesn't accumulate too many broken alleles at once.
But humans, being impatient scientists, couldn't just sit around and wait for the incredibly rare natural mutations to happen. If we wanted to understand the physical trigger of a mutation, we had to figure out a way to force a jump on demand, which leads to the use of X-rays.
This is the moment in the text where the synthesis of physics and biology truly crystallizes. The Russian geneticist Timofey Frasovsky conducted groundbreaking experiments where he irradiated fruit flies with X-rays.
He discovered that hitting the flies with X-rays drastically increased their mutation rate.
And crucially, the mutations produced were not freakish, unnatural aberrations. They were exactly the same types of mutations that occurred naturally, just generated at a highly accelerated pace.
And Timofey discovered two incredibly important physical laws governing these X-ray mutations. The first law is that the mutation rate is strictly mathematically proportional to the dosage of the X-rays.
Which tells the physicists something profound about the nature of the event. It means mutation is not an accumulated gradual effect.
Yes. If you hit the fly with half a dose of radiation, you get exactly half the number of mutations. It doesn't act like a slow poison that warms up the genes or gradually predisposes them to mutating later.
It is a binary single-hit event. One single X-ray hit causes one instant mutation.
And the second law he discovered is even more revealing. The mutation rate depends only on the total amount of ionization produced in the tissue, regardless of the specific wavelength of the X-rays or gamma rays the scientist uses.
By measuring the ionization density required to produce a specific mutation, physicists could mathematically calculate the exact physical size of the target the X-ray was hitting inside the cell.
If you are wondering how small this target really is, Delbruck, another brilliant physicist who worked alongside Timofey, did the math.
He calculated that the critical volume, the literal physical target area inside the cell that an X-ray particle has to hit to cause a specific genetic mutation, is only about 10 atomic distances cubed.
That is an unimaginably small area containing just about 1,000 atoms.
Let us walk through the physical mechanics of this. An X-ray passes through the biological tissue. Occasionally, it causes an ionization event, effectively a localized microscopic explosion of heat.
A secondary electron is produced, depositing a massive instantaneous spike of energy, roughly 30 electron volts, into an incredibly tiny space.
This localized heat wave, if it happens to hit within 10 atomic distances of a specific 1,000 atom target in the chromosome, acts as the physical trigger that instantly and permanently alters the hereditary code.
So we have a microscopic target surviving peacefully for centuries at a boiling 98 degrees, but a sudden 30 electron volt microscopic explosion permanently rearranges its structure. How do we explain this physical discrepancy?
This is the critical juncture where Schrödinger introduces the quantum solution. Specifically, he relies on the Heitler-London theory of the chemical bond to explain how the gene survives.
So if the gene is too small to rely on the safety of large numbers, how does it survive the heat of the body without melting down? This forces us to look at the physics of the molecular bonds themselves. Let's explain, like I'm 5, what is actually holding these atoms together?
Well, in classical physics, we imagine energy as continuous. You can push a block up a ramp, stopping at any height you want. You can add any small amount of energy to a system.
But in quantum mechanics, the rules change entirely. Energy is quantized. It exists only in discrete, specific levels, like steps on a staircase.
At the molecular scale, when atoms come together to form a molecule, they share electrons. The Heitler-London forces are the quantum mechanical rules governing how those electrons are shared.
These forces trap the atoms in a highly specific configuration that represents a very specific energy state.
You cannot slowly bend or gradually stretch this atomic shape. The atoms are sitting at the bottom of what physicists call an energy well.
So to change the shape of the gene, which is exactly what a mutation is, it's an isomeric transition, meaning the molecule doesn't lose or gain any atoms, it just suddenly rearranges its identical atoms into a brand new, stable geometric shape.
To do that, the molecule has to physically jump out of its current energy well, cross a barrier, and fall into a new energy well.
Precisely. And between the old shape and the new shape is a threshold of energy. Let's call the energy required to lift the atoms out of the well and cross that threshold W.
The molecule must be supplied with a specific discrete burst of energy equal to or greater than W to make the jump. It's an all-or-nothing event, a quantum jump. If it gets 99% of W, it just falls back to its original shape.
But the gene is sitting in a human body at 98 degrees Fahrenheit. There is ambient heat energy bouncing all around it constantly. Let's call that ambient heat energy KT. Why doesn't the ambient heat just push the gene over the threshold all the time?
Because of the mathematics of probability. The probability of the ambient heat randomly coalescing and focusing enough energy on that one specific microscopic spot to cross the threshold W depends exponentially on the ratio of W to KT.
Here's where it gets really interesting. Because it is an exponential function, even tiny, minuscule changes in that ratio create massive, incomprehensible leaps in the physical stability of the molecule.
Schrödinger gives some numbers for this that just blow my mind. He calculates that if the threshold W is 30 times larger than the ambient heat KT, the gene will naturally mutate in a fraction of a second. It would be utterly unstable.
But if W is just 50 times larger than KT, the gene will remain perfectly locked and stable for 16 months. And if it's 60 times larger, just a slightly deeper energy well, the gene won't mutate for 30,000 years.
This is the quantum mechanical secret of life. The atoms in the gene are locked together by strong Heitler-London quantum forces. The threshold energy W required to rearrange them is just high enough, estimated to be around 1.5 to 2 electron volts, that the ambient 98-degree heat of the human body is vastly, exponentially insufficient to trigger a change.
The gene simply ignores the thermal chaos completely because the chaos does not possess the concentrated discrete energy required to force a quantum jump. The gene is essentially frozen in a quantum state.
It is frozen, completely oblivious to the heat storm around it, until an X-ray comes along and drops a concentrated 30 electron-volt energy bomb right on top of it.
Exactly. The X-ray explosion vastly exceeds the 2 electron-volt threshold W. It instantly forces the atoms out of their well and into a new isomeric arrangement. The gene has mutated.
And once the atoms settle into their new energy well, the new shape is just as locked and stable as it was before, ready to be inherited for another 30,000 years. De Vries was right all along. A biological mutation is literally, physically, a quantum jump within the gene molecule.
Which perfectly solves the biological contradiction. The code script does not need billions of atoms to maintain its shape, using the blurry safety of statistical averages.
It can use just a few thousand atoms because it relies on the ironclad, absolute rules of quantum mechanics to lock those specific atoms perfectly in place.
If we accept that the gene is essentially a single, massive molecule securely locked in place by quantum mechanics, it completely challenges our fundamental understanding of what matter actually is.
So what does this molecule actually look like? Schrödinger tells us we need to redefine matter, because the mental image we all learned in high school chemistry about molecules is kind of wrong when applied here.
We are typically taught to think of molecules as floating freely, zipping around in gases or tumbling over each other in liquids.
But Schrödinger argues that a molecule, at its core, is fundamentally a solid. A small molecule is just the germ, the seed, of a solid object, held together by those incredibly strong Heitler-London quantum forces.
And he contrasts two completely different ways nature can build a solid. The first way is the normal crystal, like a grain of salt or a diamond. This is what physicists call a periodic crystal.
It is built by taking a very simple arrangement of atoms and just repeating it over and over and over again in 3 dimensions.
Yeah.
He compares it to ordinary wallpaper. It is a perfectly repeating, predictable pattern.
It is very structurally stable, but because it is completely repetitive, it is also incredibly dull. It doesn't hold any meaningful information.
But the gene, he hypothesizes, is in a periodic crystal. It is a solid molecular structure securely held together by quantum forces, but its pattern does not repeat.
Every single atom, every specific group of atoms, is deliberately arranged in a unique, non-repeating sequence.
He compares the gene not to wallpaper, but to a masterpiece of embroidery or a Raphael tapestry. There is no dull repetition. It is a coherent, deeply meaningful, incredibly complex design where every single thread plays a vital role.
And conceptualizing it as a periodic crystal elegantly solves the final mystery of the code script. How can something so incredibly small hold so much vast information?
To illustrate this concept, Schrödinger uses the mathematics of information theory and density, specifically looking at the mechanics of Morse code.
Think about Morse code. It uses only 2 symbols, a dot and a dash. If you restrict yourself to making groups of 4 symbols or less, you can make 30 different unique letters or commands. That is how the alphabet is coded.
But what if you added just a 3rd symbol? And what if you allowed yourself to use groups of up to 10 symbols in a row? Suddenly the math explodes. You would have over 88,000 unique combinations.
Now apply this mathematical logic to our biological aperiodic crystal. Let us imagine the gene is built from just 5 different types of molecular groups analogous to 5 different symbols.
If you arrange them into a single linear sequence of just 25 symbols, how many unique structural combinations can you create?
Over 62 trillion.
62 trillion unique combinations from a microscopic string of just 25 atoms or molecular groups. A single actual gene contains hundreds or thousands of atoms. Therefore, the number of possible uniquely stable quantum arrangements is practically infinite.
This mathematical reality proves that a tiny aperiodic solid can easily, comfortably hold the unimaginably complex architect's plan for an entire human being within a microscopic volume. The aperiodic crystal is the ultimate, infinitely dense hard drive.
Okay, so we have brilliantly solved the micromystery. We know how the incredibly detailed genetic blueprint is physically stored as an aperiodic crystal, and we know how it survives the boiling thermal chaos of the body by being locked into a rigid quantum energy well.
But as we zoom out, we hit an even bigger problem, because it is great that the microscopic blueprint is safe, but how does the actual macroscopic human body, this giant, walking, breathing mass of trillions of atoms, avoid decaying into thermodynamic sludge?
This requires us to confront the most depressing law in physics, the second law of thermodynamics and the inescapable concept of entropy.
Let's clearly define entropy for you listening. Entropy is basically the mathematical measure of disorder in the universe, right?
Yes. Mathematically, it is expressed in Boltzmann's famous equation. Entropy equals K times the logarithm of D, where D is the quantitative measure of atomistic disorder.
The second law of thermodynamics states a cruel truth. Everything in the universe naturally, inevitably tends toward maximum entropy. It tends toward chaos, uniform temperature, and dead equilibrium.
If you leave a hot cup of coffee on a table, it cools down until it matches the room. If you stack a neat pile of papers, the wind scatters them. Without continuous outside intervention, order always undeniably decays into disorder.
And when a living biological organism eventually reaches maximum entropy, that state of complete dead equilibrium is called death.
Precisely. Thermodynamical equilibrium is physical death. So what is the characteristic defining feature of life? It is the ability of an organism to continuously evade this rapid, natural decay into equilibrium.
Think about your body right now. You are constantly moving. Your heart is generating heat. Your cells are breaking down tissues, all of which produces massive amounts of positive entropy. You are constantly generating internal chaos just by the mechanical act of being alive.
So how do we stay alive? The obvious answer we are all taught in grade school is we eat. We have a metabolism. But Schrödinger points out something incredibly insightful and slightly hilarious about this. He says the way we look at a calorie menu card in a restaurant is conceptually absurd.
It is absurd if you analyze it purely in terms of material exchange. The word metabolism literally translates to exchange. But what physical material are we actually exchanging?
An atom of nitrogen in a piece of chicken you eat is physically atomically identical to an atom of nitrogen already in your own muscle tissue. There is absolutely no biological advantage to simply swapping one identical atom for another.
And even if you try to argue, well, we don't eat for the atoms, we eat for the energy, that doesn't fully make physical sense either, because an adult human's energy content is relatively stationary.
Over the course of a day, we take in energy as food, but we give off the exact same amount of energy back to the environment as heat and motion. We aren't a battery that just infinitely charges.
So if we aren't just hoarding material, and we aren't just hoarding energy, what is the precious, vital something we are extracting from our food to stave off thermodynamic death?
We are feeding on negative entropy.
Okay, we need to carefully explain negative entropy because that sounds like science fiction.
It is deeply logical. If entropy, mathematically written as K log D, is the absolute measure of disorder, then if we put a negative sign in front of it, creating negative entropy, or K log of 1 over D, it becomes a direct mathematical measure of order.
Living organisms maintain their incredibly complex, highly improbable, low entropy state by continually sucking orderliness from their surrounding environment.
Consider the last meal you ate. When you eat a salad or a piece of steak, you're not just eating atoms or calories. You are literally physically consuming the order of the universe.
Exactly. You consume extremely well-ordered matter, the complex cellular structures of plants, the highly organized tissues of animals. Your body digests them, extracting the chemical orderliness from those complex bonds to reconstruct your own failing cells and maintain your delicate low-entropy state.
And then you excrete the remnants in a highly degraded, vastly high-entropy disordered form. You are effectively acting as an incredibly efficient biological entropy vacuum.
You pull exquisite order from the universe, use it to repair your internal machinery, and dump your internal chaotic waste back out into the environment.
But wait, I have to push back here, because Schrödinger actually includes a brilliant addendum in the text. A colleague of his named Simon read this manuscript and pointed out a logical flaw.
Simon said, "Wait a minute, Irwin. If the only thing the human body needs to survive is pure physical order, why can't we just eat unburnt coal or drink diamond pulp?"
A diamond is a perfectly ordered, beautifully structured periodic crystal. It has massive negative entropy. Why doesn't eating a diamond keep me alive?
It is an excellent, incisive critique, and Schrödinger happily concedes the nuance. We cannot survive on diamonds because we do still require the specific, accessible chemical energy locked within complex organic compounds.
Why? Because we need to replace the mechanical energy we expend by walking and breathing, and crucially, we desperately need fuel to generate continuous body heat.
Which feels like a paradox. Generating heat seems counterproductive if we just established earlier that heat causes thermal chaos and disorder.
But giving off heat to the surrounding environment is the exact primary mechanism by which an organism successfully dumps its surplus positive entropy. It is the exhaust pipe.
You generate heat internally, that heat radiates off your skin into the room, and as it leaves your body, it carries the physical disorder away with it into the atmosphere.
But to continuously generate that necessary heat, you need combustible fuel. So you cannot eat diamonds, they do not burn in the body. You must eat highly ordered combustible organic matter.
Plants capture the ultimate source of negative entropy in our solar system, sunlight, and weave that raw order into combustible sugars. We eat the plants, or we eat the animals that ate the plants, extracting that order, burning the fuel, and radiating our chaotic heat back out into the cold universe.
So we step back and look at the whole incredible picture. We have solved the micro level. The biological blueprint is in a periodic crystal safely locked away by quantum mechanics.
And we have solved the macro level. The massive biological organism survives by acting as a vacuum, sucking negative entropy from the universe to fight off thermodynamic death.
So what does this all mean? Does this ultimately mean life is just one big, complicated, determinative physics equation?
We have reached the grand reveal of Schrödinger's synthesis. Studying the living cell does not merely confirm the existing laws of classical physics. It reveals entirely new laws of physics at play in the universe.
Up until this point in the deep dive, all the classical physics we have talked about, paramagnetism, diffusion, the square root of n rule, was based entirely on one single mechanism: order from disorder.
You take millions of chaotic, totally disorderly atoms, and through the sheer brute force of statistics, you average them out into an orderly, predictable, macroscopic physical law.
But life does not operate primarily on that brute force principle. The living organism relies on an entirely different, incredibly elegant mechanism: order from order.
To explain the profound difference here, Schrödinger asks us to compare the living cell to a piece of clockwork. Think about a beautifully crafted brass pendulum clock, or even the motion of the planets in the solar system.
They move with absolute, predictable, deterministic precision. They do not seem to care about the chaotic heat motion of atoms or statistical averages at all. Why do they get to ignore the chaos?
To understand that, we must look at Nernst's theorem, also known as the third law of thermodynamics. This law states that at absolute zero, molecular disorder ceases entirely. All thermal chaos stops.
Now, obviously, a pendulum clock sitting in your living room is not at absolute zero. It is at room temperature. But the clock is built of solid brass and iron, meaning its atoms are rigidly locked together by those incredibly strong Heitler-London quantum forces.
The exact same quantum forces holding the genetic aperiodic crystal together.
Precisely. Because the quantum bonds of the brass are so immensely strong, for the solid gears of a clock, room temperature is virtually absolute zero.
The ambient heat energy bouncing against the gear is so pathetically weak compared to the structural integrity of the metal that the disorder is effectively negligible.
Therefore, the clock operates dynamically and deterministically. The orderly movement of one gear directly causes the orderly movement of the next. It produces order from order, completely bypassing the need for statistical averages.
But a human-made clock is coarse, it is clumsy, it still suffers from microscopic friction, it loses energy, the metal eventually wears down, and the clock stops.
Yes, human engineering is inherently flawed, but the living cell is a flawless quantum clockwork. The organism is driven by the aperiodic crystal, the gene, which Schrödinger calls the finest masterpiece ever achieved along the lines of quantum mechanics.
Unlike a coarse metal gear, the chromosome is a single, perfectly structured atomic association. It operates on a principle utterly unprecedented in the entire scientific study of dead matter.
We have a microscopic, single copy of a biological instruction manual that perfectly dictates the incredibly ordered, deterministic, dynamical behavior of a macroscopic entity composed of trillions of cells.
So the grand new law of physics that life reveals to humanity is this dynamical order from order principle scaling all the way up from the microscopic quantum level to the macroscopic visible level.
It is a breathtaking realization.
But Schrödinger does not stop there. He takes this biological reality, and in the epilogue of the book, he pushes it to the ultimate staggering philosophical extreme. If we logically accept that the human body is essentially a glorious, infinitely complex quantum mechanical clockwork driven by the inescapable deterministic laws of physics, we are forced to ask a deeply uncomfortable question.
What happens to free will? What happens to the entity you call I?
He lays out a devastating logical trap for the reader consisting of two premises. Premise one, my body functions as a pure physical mechanism according to the laws of nature. It is a clockwork.
Premise two, I know, by incontrovertible, undeniable direct personal experience, that I direct the motions of my body, I foresee the effects of my actions, and I take full moral and ethical responsibility for them.
How do you possibly resolve that glaring contradiction? If you are ultimately a machine following quantum rules, how can you be responsible for anything you do?
The inevitable, staggering philosophical conclusion Schrödinger draws to escape this trap is this: Deus factus sum. I have become God.
That is a massive statement.
It sounds incredibly blasphemous when viewed through a traditional Western religious context, but he is speaking deeply philosophically. Follow the logic. If the unyielding laws of nature control the motion of the atoms, and I indisputably control the motion of my body, then I must be the entity that controls the motion of the atoms.
The consciousness that refers to itself as I is the prime mover. It is the author of the laws of nature themselves.
He connects this realization directly to Eastern mysticism, specifically drawing heavily from the ancient Indian text, the Upanishads. He points to the central concept that Atman equals Brahman, the idea that the personal, individual self is actually physically identical to the omnipresent, all-comprehending eternal self of the universe.
Western ideology is fundamentally obsessed with plurality. We look around the world, we see billions of different human bodies walking around, and so our intuition assumes there must be billions of different separate souls or individual consciousnesses.
Schrödinger, echoing the Indian philosophers, calls this assumption the ultimate illusion. He refers to it as Maja.
He uses this beautiful, evocative analogy to explain why plurality is an illusion. He calls it the gallery of mirrors. He says looking at consciousness is like looking at a mountain range. From one valley in Nepal, you look up and you call the peak Mount Everest.
From another valley in Tibet, you look up at the peak and you call it Garrison Car. You have two different names, two different perspectives, but it is the exact same rock.
Consciousness, he argues, is a singular tentum, a grammatical term for a singular noun that literally has no plural form. There is only one single consciousness in the entire universe, and it is just experiencing itself simultaneously through the billions of different biological mirrors of our individual bodies.
He asks the reader to truly, deeply analyze what the I actually consists of. We so often mistakenly think the I is our collection of memories or our specific personality traits.
But those change constantly. The personality and beliefs of a 16-year-old are completely different from the personality of an 80-year-old. A skilled hypnotist can temporarily wipe your memories.
If you suffer a traumatic brain injury and get amnesia, you lose your past. But your I, your sense existing in the present moment, does not die.
Because the I is not the paint on the canvas. The paint can be scraped off and repainted. The I is the blank canvas itself upon which all those experiences and memories are collected.
And because there is only one universal canvas in existence, there is no intermediate break, no actual end, when a physical biological body inevitably fails. Therefore, from a physicist's perspective, there is no real, true death of the personal existence.
It is a profoundly moving, deeply unifying vision of reality. And what is so remarkable is that it is not based on wishful thinking. It is built meticulously, step by step, upon the rigid bedrock of quantum physics, thermodynamics, and genetics.
What an absolutely unbelievable intellectual journey. We started this deep dive looking at the violent, chaotic, unpredictable storm of atomic heat motion.
We zoomed deep into the microscopic, quantum-locked Raphael tapestry of the genetic crystal, sitting totally undisturbed in the boiling heat of the cell.
We zoomed back out to watch the massive, macroscopic organism continuously sucking pure order from the universe just to fight off thermodynamic death.
And finally, we realized that the consciousness driving this incredibly complex, beautiful quantum machine is a singular, universal phenomenon.
It is a perspective that fundamentally alters how one views their own existence and their place in the physical world.
It really does. And I want to ground this entire theoretical discussion back to you, listening to this in your everyday life. Consider the next time you sit down for a meal. Look closely at your food before you eat it.
Realize that you aren't just eating empty calories or basic chemical fuel.
You are literally, physically consuming the organized structure of the universe, extracting the negative entropy woven originally by the power of the sun, all just to keep the incredible quantum clockwork of your body ticking relentlessly against the chaotic decay of time.
And we want to leave you with one final, deeply provocative thought to mull over, building directly on the profound philosophical implications of Schrödinger's epilogue.
If human consciousness is truly a single universal canvas, and the persistent illusion of separate souls is just a trick of the light reflecting off our different biological mirrors, how does that change the way you look at a complete stranger on the street?
Think deeply about that tomorrow. If Schrödinger's physics and philosophy hold true, that random person looking back at you from across the room isn't a separate entity at all.
They are literally you. They are just experiencing the exact same universe from a slightly different valley. Thank you so much for joining us on this deep dive. Remember, the relentless pursuit of knowledge is the ultimate way to feed your mind on negative entropy. We will see you next time.